Okay, so this is for question 11 of chapter 3 of an introduction to statistical learning. This video is done in Python. I've already made a video in R, so choose wisely. This is a multi-part question, and it goes from A through F, and all the questions are listed here. But we'll go through them just as they come up instead of looking at all the questions ahead of time. This first block of code we need to run. So I need to import numpy, and I'm going to generate an x variable and a y variable. Okay. So for the x variable, I'm using a random number generator. For a normal distribution, I'm generating 100 values from that distribution. And then I'm doing the same thing for y, but I'm adding 2 times whatever the corresponding x value is, right? So y should be about twice as big as x plus some noise, all right? With this command up here, we are in R, this command is called set seed, and a seed for random number generation is a value. So when these programs are generating random numbers, they aren't truly random, but they are pseudo-random, and so it takes a seed number and then operates on it with some mathematical magic and outputs a number that seems random. And so by setting that seed to a particular value, in this case 1, it will always give you the same results if you use the same code on it, right? It generates the same random numbers, if that made the same pseudo-random numbers. Okay, so if you run this and you use 1 for this value, you should get the same values that I get here, but it also seems possible that there are maybe differences between Python versions, or Python will update and change a little bit, but anyway. Yeah, okay, so I've already ran that, so I've generated my x and y variables. Now the first thing that, here's some more stuff that we want to install. Actually, I don't think that we need the ISLP, we don't need that package, but we do need this, the ones that are listed here. Well, actually, some of them. It doesn't matter, it doesn't hurt to have them. Okay, so the first thing that we want to do is to regress y onto x without an intercept. Okay, and then we're just going to look at the output for now. So here's my model, my object, okay, and so I'm going to use the OLS algorithm of y onto x, and it says to do it without an intercept, and in Python, it's just assuming that you're not using an intercept, right? We have to actively tell it to use an intercept. This is opposite of R, so if you go to R, you'll notice that it's that you have to specify don't use an intercept, but here we don't have to specify that. So I'm going to run that, okay? And here's our output, and there's not much to comment on just yet. But I will make one comment. If you watch the R version of this, you'll notice that these values are a little bit different than the R video. And I should mention this. Why is that the case? So don't pound your head if you can't get the 2 versions to work correctly. It's because they're using a different, they're using a different algorithm to generate the random numbers that generated the data. So you're working with different data in both cases. Okay. Okay. Anyway, that's our output for this first model, and now we're going to do the same thing, but instead of regressing y onto x, we're regressing x onto y. Again, no intercept. All right. So here we are, and now notice. In part C, we want to compare we want to look for a relationship between the 2, okay? Well, let's look for some relationships here. So in the first one, where we regress y onto x, we notice that y is about twice as big as x, which is, we should expect that, okay? That's how we made the data. But also notice the t and p values here are identical in the reverse. Okay, they're in the reverse regression, all right? These are identical values. Okay, so we're going to explore that a little bit in the next questions. Okay. Part D wants to do an algebraic proof in which we show that the t-statistic, which is given here, is equivalent to this guy here. All right, so I'm obviously not going to run through every step of the proof here, but you should check, or you should try to do it yourself. I have my answer here. You could even check my work to make sure I have not made an error. But in the end, following through all these steps, you come to this guy right here. Okay. As part of this question, we also want to check this numerically. All right. So how are we going to do that? So here I have an expression written out in longhand. I have this expression. Okay, I have this expression written out in longhand. Okay, and I'm going to, so that's going to give us presumably the t-statistic for our xy. Actually, I think I want yx for our yx regression that we did earlier. Okay, and so again, I have my t-statistic, and it is identical to what we calculated here. Okay, so we've showed it algebraically, and we've showed that the algebraic one is equivalent to the numerical one. Okay. Now in part E, we want to argue that the results we got from part D, right, this whole guy, would be equivalent to regressing x onto y, right, instead of y onto x. Okay, so the easiest way for me to think about this is if I go to my proof here, everywhere you see an x, put a y, and everywhere you put a y, put an x, and then just chug through the proof again. Well, x and y are just simply labels, and so at the end we should come out with the same expression. Okay. All right. Okay. Finally, in part F, we again are regressing y onto x once, and then x onto y, but this time we are using an intercept, and again we want to compare the t-statistics. Okay. So again, in Python, we have to specify that we want to estimate an intercept, and so I need to create a different set of data where I take x and I add a constant, right? And the ordinary least squares is going to act on that constant to estimate the intercept. Okay, so I have my two new models, right, where I'm using the intercepted value for the predictor variables x1 and y1. Okay. I'll get the results, and I'll print the summaries of the two. Okay, so this top part is the regression of y onto x, and the bottom one is the regression of x onto y. Okay, and if I go to the t-statistics and p-values for the coefficients, again they are identical. Okay, unfortunately, Python uses x1 as the name of the coefficient in both of these, but in this one it should just be x, and in this one it should be y. x1 is just a generic name that it gives to it. But again, the important part is even with the intercept being estimated, we get the same t-statistics for the coefficients. Although notice not for the intercepts. Anyway, okay, that is it for this one.